Hi, Mick McQuaid here. I'd like to talk to you a little bit about the internet and to give you some definitions about the internet. And that may seem very trivial in 2017 because we use the internet all the time. It's like water or power. It's pervasive. So we all have a common understanding, but we're still going to need to articulate a definition that we'll use to support our later conversations in class and potentially beyond this class, depending on how much you think about the internet and how much your work involves the internet. So I want to start out by defining the internet in two ways. The first way is extremely high level, very high level, and then the second way is in a little bit more detail. So that high level definition is going to say that the internet consists of a set of agreements and hardware and software and traffic, which are packets of information that travel across the hardware and software as long as the hardware and software abide by the agreements. So that's a very simple definition of the internet. 4 elements: agreements, hardware, software, and traffic in the form of packets. That simple definition is enough for us to begin with. And in particular, it's enough to tell us what direction we would have to go in if we want to get a more detailed definition. If we want to have a more detailed definition of the internet, what we need to do is to go in one of those 4 directions so we can, for example, get more details about these agreements. And that's actually what we're going to do. These agreements are called protocols, and they are the critical thing to understanding the internet. The hardware and software change all the time. As long as they adhere to these agreements, hardware and software can change all the time, and the only effect on the internet is that traffic moves faster. So we'll have to talk a little bit about traffic, a little bit about the packets that flow across the hardware and software, but mainly we're going to talk about these agreements, which I call protocols. So that's up next. Now I'd like to talk a little bit about the agreements, or protocols as I call them, and to say a little bit about their history, how they were developed, how people use them, and to ask a few of the kinds of questions, examples of the kinds of questions that people would ask on an exam or a quiz. For any 2 computers to connect, they must agree on a pattern of 1s and 0s to use to transmit and receive, and this agreement is called a protocol. And there are all kinds of protocols. And in early history of computing, protocols were developed and owned by firms. They were important intellectual property of firms. And at that time, IBM was the size of the rest of the computing industry put together, so their main connection protocol was the main connection protocol. And this created a problem. IBM had an outsized role in connecting computers, and lots of people wanted to be able to connect without the influence of IBM. And in particular, the United States Department of Defense wanted protocols that would not be controlled by any particular company, not so much IBM, but any company that might assume the mantle of IBM. So as history has passed, IBM is no longer the dominant firm. For a while, Microsoft was the dominant firm. Now you could argue that the dominant firms are Google, Facebook, and Apple and Amazon, and in the future some firm might be dominant. The idea is to have no one single point of control, and so for connection of computers among branches of the military, some universities, and some high-tech firms, the Department of Defense paid for initiated projects that led to the internet. And there's plenty of history online about the internet. I don't need to go into the details of it. I just want to stick to the protocols. And the protocols that constitute the internet are typically called TCP/IP, or the TCP/IP suite, or the TCP/IP protocol suite. And TCP/IP stands for Transmission Control Protocol / Internet Protocol. And it is by far the most widely used protocol today. And I mean by far the most widely used computer protocol used today, and it's used by you every time that you use a computer or a phone or a tablet or a car, for that matter, or a refrigerator or any of many other appliances that are connected to the internet. And this set of protocols has been widely expected to die and be replaced by something else every year for a little over 30 years. And yet it has endured. And I've been lecturing for many years saying that it's about to be replaced by something better, and that just never happens. So now I say that with a little bit of concern that it has to happen sometime, but it hasn't happened yet. The TCP/IP protocols were or are developed by committees representing the military, branches of the military, different colleges, different high-tech firms, and individuals. And committees issue documents called Request for Comment number, where NNNN is a number that identifies the document. So, for example, one might be called RFC 1122. And actually, RFC 1122 is a real RFC. It's a famous one that outlines some important principles that take precedence over specific layers. And I'll explain in a little while what I mean by principles and layers. And an RFC, or a request for comments, becomes a standard when the comments stop and the language in the request for comments stabilizes and people rely on it. And there's no fanfare, there's no announcement, there's no certainty except by waiting to see what happens, or actually by participating, by becoming part of what happens yourself. Now, any computer or phone or car or refrigerator or whatever that behaves according to the TCP/IP protocols is on the internet. And it is fair to say that the internet is this set of protocols and nothing more, and that any piece of hardware and software can be made to follow the protocols and communicate with any other that is on the internet. Well, that's not exactly true. I don't want to get into this too much, but at an earlier phase in history, we can say that no one controls the internet. Nowadays, it is harder to say that no one controls the internet. Various nation states have tried to assert control over the internet, and that's a controversial topic. So for this class, what I'd like to do is stick to a non-controversial claim, which is that the TCP/IP protocols were designed so that no one would control the internet. That's the intention of the design. Since the internet can be thought of as a set of rules, you can imagine altering any given network to conform to those rules, and then that network being connected to all the other networks that together constitute the internet, if only that were true. So what's happened historically is that lots of networks shifted to the internet by adding hastily written undocumented software patches that relied on other software, because very little software stands alone. Most software in the world is connected to other software. And so when people who wrote patches retired and left no documentation behind, some software was updated and some software that depended on it was not updated. And so network connections to the internet started breaking. And over time, this has led firms to ditch existing networks in favor of more standardized connections to the internet. Not because that's the only thing that's possible, but because the typical software practice has made other approaches unreliable. The Internet Protocol Suite refers to the protocols that are required to connect to the Internet, and the main protocols are the Transmission Control Protocol and the Internet Protocol. But there are also other protocols for email, for file transfer, for other activities. Some of them are more low-level activities like ICMP or Internet Control Message Protocol, and some are more visible to an end user like Simple Mail Transport Protocol, which you use in your email probably every day. Since the internet was originally meant to be used by a small homogeneous group of military, college, and high-tech firms, its protocols were more limited than now, as the role of the internet has expanded over time. And the architects of the internet were interested in principles rather than layers. And not everybody agrees that principles are more important than layers, but the principle advocates mostly won out. And the fact that the principle advocates mostly won out is what has led to the growth of the internet. So I want to say a little bit about the principles before we talk about layers. The two most important principles are super, ultra, mega, just incredibly important, and these are what caused the internet to be successful and what have caused the internet to grow fast for a long time. And the two principles I call here the end-to-end principle and the robustness principle. So the end-to-end principle says that the internet should focus on speed and simplicity and should not retain any state information. that every transaction is dependent of every other transaction, and that maintenance and intelligence should be put at the edges of the internet, so that what's in the internet is very simple and very fast. And that may seem a little bit difficult to understand, the expression particularly state information. So let me give you an example. Let's say that you visit a website and you log into that website. It might be better, instead of having the website maintain memory, or having some internet protocol maintain memory that you are now logged in, for every single HTTP request that you send, in other words, every URL that you send will have a token added to it that indicates that you're logged in, and that token should be hard to forge, so that every time that you click within a website that you're logged into, you're actually resending a certain kind of login information. So that's what we mean by retaining no state information, that the website doesn't remember that you were logged in. Every time that you click, that click tells it that you're logged in. The other principle, the robustness principle, is one that's probably familiar because it's true in many walks of life, many fields, many disciplines. The very basic idea to be conservative in sending and liberal in receiving. And so that means to be careful to send well-formed datagrams, but to be willing to accept any datagram whose meaning is clear, even if it has technical errors. And the other aspect of the robustness principle is that you should never exploit legitimate but obscure protocol features that other internet nodes are too deficient to handle. So don't get too fancy with the internet. Just do the basics on the internet. And those design principles kind of won out and made it possible for the internet to grow really fast without breaking very much. Layers do play an important role, though. And this is because different technologies advance at different rates. So if someone invents something, do you think that they should have to wait for everyone to catch up before they can use it? Probably you don't. Probably you think that people should be allowed to invent as fast as they can and add things, buy computers and phones and tablets and so on as fast as they are legitimately improved. And so what happens is, for the way that this works on the internet, is that everything that the internet does is divided into layers, and every layer has its own thing going on, and all that it has to know about is the interface to the layer above it and potentially to the layer below it. And so an advance in technology in one layer doesn't change the interface to the layer above it or potentially the layer below it. And so the advance in technology can proceed without disrupting the rest of the internet. So the convention is, we call the top layer the layer that connects to humans, and we consider the bottom layer to be sort of where the data travels through a network. It's a little bit more complicated than that, but it's sufficient for our discussions to think of it that way. That the top layer is the most human, the bottom layer is sort of the most internety, and if that is a word. And we'll consider basically a four-layer model between human and hardware. And those four layers we're going to call application, transport, internet, and link. Now imagine that everything that you do in an internet connection, and I'm going to use the example of sending an email. So everything that you do goes from the top layer at one end of a connection to the top layer at the other end of the connection. So let's say you click to send email, and your click sort of goes down through the layers at your end, across the internet, and back up the layers at the other end. So let's take a look at that path in a little bit more detail, but still in a simplified way. So here's a diagram of that concept, and I should point out that although I photographed it with enough detail that you can read the caption, there's a bizarre typo in the caption, so don't take the caption too seriously. Anyway, the main thing that I want you to think about are these blocks which represent the layers. So you can see on the left side, let's say that's the beginning side, we have the HTTP block, or the HTTP layer, we could say, and then below that the TCP layer, the IP layer, and then going across we have more of the IP layer, and then coming back up we go from the IP layer to the TCP layer to the HTTP layer. And above that, we see pictures of computers and different kinds of network hardware. So you may have in your office, for example, a token ring network. You're much more likely to have an Ethernet network. You certainly have routers. It's possible that you have dial-up links. That's a little bit more rare. But anyway, all those forms of hardware don't really matter. You can have any sort of hardware between these two computers because they all obey the internet protocols. Down at the bottom are the names of the individual technologies: token ring again, PPP, Ethernet, and Ethernet. And those particular technologies don't, as I say, matter much. Some are more common than others. For example, Ethernet is very of all of those, Ethernet is the most common by far, but they don't matter as long as they obey the Internet Protocol suite. So the beginning of the traversal is going down through the layers. So that click that you made to begin the process goes down through your layers, and each layer adds a wrapper around your original content. And that wrapper includes some ones and zeros at the start of your content and some ones and zeros at the end of your content. One layer, which we'll call the transport layer, divides your content into packets and puts a wrapper at the beginning and end of each packet, and the layers below that only ever deal, the internet layer and the link layer, only ever deal with the packets. And this is an important reason for the speed of the internet, is this packet orientation. At the bottom layer, the link layer, it gets sent through your network to your network's connection to the internet. Once your packets get to the internet, they go back up one layer, and the outer wrapper is stripped off of each packet. And at that layer, it travels across the internet to another network where it goes back down to the link layer. Now, ideally, that network is where the final destination lives, and this stage of the traversal is over. But it may not be, and the different packets will likely follow different routes. They'll go through the different pieces of your email, and these are very tiny, tiny pieces of your email. They may travel through many different paths to reach the final destination network. So whatever network it goes to next, it goes through that network to the boundary where it meets the internet and that is closest to its destination, and then it crosses the internet again and repeats the above process until it reaches the final network. Once inside the network of the recipient, the link layer puts on a wrapper that associates the internet protocol address with a particular unique machine address and sends it through the network, through this particular network, to that particular machine. And at the destination machine, each packet goes up through the layers, stripping off wrappers, reassembling packets into content, and arrives at the destination, which is the application layer, where it is seen by a person or by a program. You know, you can send email to programs rather than, increasingly now, to programs rather than people, but whatever or whoever is the ultimate recipient. Encapsulation is the term used to describe how each layer does its own thing, and only the interface from one layer to another is standardized. So we'll talk about 4 layers, but some people think there are or should be more layers, or that the layers should be more rigidly defined. But 4 is enough for this class and describes the actual internet very well. There are competing models like the OSI model that have more layers and more rigidly defined layers, and they are supposed to replace the internet, one of these competing models. But they failed to replace the internet for 30 years, so I'm not really that interested in talking about them. Again, the 4 layers that we talk about are the link layer, the internet layer, the transport layer, and the application layer. The bottom layer, the link layer, is the one that sends packets through a given network. It does not know what is in the packets. It knows how to hop from one place to another in the direction of its goal, and that's all that it knows. It knows about Ethernet, it knows about Wi-Fi, fiber optic, cellular radio, or whatever medium through which a device can connect to an individual network. The internet layer, one layer above that, knows only that there are different networks in the internet and how to traverse the boundaries between those networks. It does not care about how the individual networks are laid out. It knows which network of the networks it connects to is closer to the destination of a packet. That's it. And this is where IP addresses are defined, and we're going to have to talk a little bit more about IP addresses. IP addresses, or Internet Protocol addresses, were defined in version 4, which is what we use. This is the most common standard. Defines addresses of 32 bits in length, and you can see a long 32-bit number here. And these addresses are represented in 4 groups of 8 bits each. So, for example, here's my current address. This is the address of my machine in my office. 1000, and so on. And these addresses are usually represented in displays designed for people as decimal numbers from 0 to 255 separated by dots. So that 32-bit address is usually shown as 129.21.217.106 for human consumption. That's my internet address. Any internet traffic destined to reach me will be a series of ones and zeros that include that pattern in designated parts of the series. Now there is a new standard called Internet Protocol version 6, which we are supposed to change to, and we're eventually going to have to because we're running out of addresses. So currently everyone who uses it also uses IPv4, Internet Protocol version 4, because currently there are sort of enough addresses. But we are running out of addresses, and sometime soon we'll be using this completely different scheme. The IPv4 scheme has many features, including masking. So this is an example of working with an IP address. So it has many features, including masking, that allow decentralization of control. See, remember, one of the main aspects of the internet is that there should be no control in the internet. The internet should just be able to flow. This is part of the simplicity and robustness, or not the robustness, just the simplicity of the internet. Make things as simple as possible and as fast as possible. A lot of simplicity has to do with speed. Increasing speed and eliminating control allows us to allows traffic to flow faster through the internet. Let's put it that way. Masking means to manipulate bits in a simple way, analogous to how masking tape marks a physical region that you don't want to cover with spray paint. And masking consists of 4 things. It consists of a masking operation, an input series of bits, an applied series of bits, which is the mask, and an output series of bits, which is the result of the masking operation applying a mask to an input series of bits. So we have then the result is an output series of bits. Okay, now if this were an undergraduate class, I would actually ask you these details. In a class like this, I just want to go over the concepts. I want you to have a grasp of the concepts, and it's sort of up to you to decide how much detail that you want to have at your fingertips. But I do want to expose you to this. So in particular, I want to expose you to these 3 kinds of masks, AND, OR, and XOR. And you can find a detailed article about them, a good article on Wikipedia. Quite a lot of the Wikipedia articles, by the way, on beginning computing concepts are good articles. A lot of the more advanced articles are not so good. They get into controversies and they take a stand on controversies without letting you know that they're taking a stand on controversies. So there can be some issues with using Wikipedia. But this is an example of where I think Wikipedia shines. Anyway, in the article, they use Y as the current value of an input bit. So the input bit is always either 0 or 1. So let's look at OR, AND, and XOR. So OR uses the principle that Y or 1 equals 1 and Y or 0 equals Y. So if Y is that's the input bit. So if Y is a 0, it turns it into a 1. If Y is, assuming that the mask is 1, if Y is 1 and the mask is 1, it becomes 1. If Y is 0 and the mask is 0, then Y becomes 0. If Y is 1 and the mask is 0, then Y stays 1. And uses the principle that, and these are just basic logic operators, so you may have encountered these in math classes before, or logic classes. So the principle that Y and 1 equals Y and Y and 0 equals 0 leads to the first one leaving a 1 bit as a 1, while the second one turning a 1 bit into a 0, and they both leave 0 as 0. XOR uses the principle that 1 XOR 1 equals 0, and 1 XOR 0 equals 1. So this flips a 1 bit to a 0, and the second one flips a 0 bit to a 1. Now, by now you might be wondering how do we actually use masking? Why do we actually care about masking? Well, a very common masking operation that is used, that you use every day without knowing it, of course, is to mask the third and fourth octets in your IPv address so that only the first two octets are recognizable and the last two are set to some standard. So a masking operation that would accomplish this would be an OR operation that takes an address and a mask as input and returns a masked address as the output. So the input series of bits in this case would be my IP address, which I've already told you is 129.21.217.106. The mask, and by the way, you can easily find out your IP address on any computer. It's not a mysterious thing if you know the correct instructions to give the computer. So the second thing is the mask to hide my particulars. And so what I want to do, my particulars, you can sort of think of, by the way, 129.120.21 as my street address and the 217.106 as my apartment number. So my particulars are 217.106. And instead I would like this to be delivered to, say I want it delivered to a building-wide address, which is a building-wide standard service. So the mask that I would use here is 0.0.255.255, and the output series of bits in this case would be the masked address 129.21.255.255. And if you take a look at the headers of your emails, you'll find addresses like this in them. IP addresses at one time, before the internet became popular, were given out in a scheme that involved 5 classes, 3 of which require some masking. So class A uses only the first octet of the IP address, and these IP addresses were given to the internet users most likely to have the most nodes, that is, like the most computers, the most users, because they could hand out the other 3 octets as they saw fit. Class B addresses used only the first 2 octets of the IP address. So RIT receives such an address, which is 129.21. So any mail traffic destined for a 129.21 address is destined for RIT. And there are only 256 times 256, or 65,536 Class B individual addresses possible. So that means that RIT only has 65,536 addresses to give out, and those are the addresses that are quickly running out because, I mean, we have thousands of people at RIT. If each one of them has a smartwatch and a smartphone and a tablet and a computer, you can easily imagine how quickly we use up those addresses. So anyway, so these addresses were given to users likely to have a lot of nodes. A lot of major universities have these kinds of addresses. You can sort of identify the university by the first 2 octets. Class C addresses use only the first 3 octets, leaving the user free to assign 256 nodes within that block of IP addresses. So those were given to people or firms or organizations that were not expected to ever have very many IP addresses. At that time, this is in the early days of the internet. Now, after 1993, this scheme was dropped, but we still use subnet masking every day for certain purposes. For example, at RIT, we have a bunch of subnets, like subnet number 1 has addresses from 129.21.32.1 to 129.21.63.254. So every number in between that is part of subnet 1, except that there is a special pair. There's a rule. So there are lots and lots of rules, and one of these rules is that there's a special pair of IP addresses that prevent you from using 0 or 255 as the 4th octet. That's the reason that the numbering is from 1 to 254. So 0 has a special use in the 4th place. 0 has a special use, and in the 4th place, 255 has a special place. And the special rules apply to all the addresses in between. So the above series goes up to 254 on the 32 network, and then skips to the 33 network, skips 2 addresses to the 33 network and the number 1 address, skipping the 2 forbidden addresses. So if I use the subnet mask 224, the above range of addresses will resolve to subnet 1. which is 129.21.32.0. And that address leads to the router, which is a specialized computer usually made by Cisco. That's the most the dominant router builder today, that routes packets to any of the 254 machines that are on subnet 1. The transport layer knows where different network-related things are on your computer, and it knows about the endpoints in a connection, but nothing about the networks in between the endpoints. So it knows how to make the transmission of data to the endpoint reliable. And it knows how to divide your content into packets with information about their final destination and the sequence in which to reassemble them so that your email, for example, comes out all in the right order. The top layer is where the content is created and specified. So this is what you would be familiar with. And the content could be email, for example. It could be files. It could be dialogue between computers. It could be web pages, or quite a few other things today. And each of these abbreviations represents a protocol. SMTP is Simple Mail Transport Protocol, FTP is File Transfer Protocol, SSH is Secure Shell, and HTTP is Hypertext Transfer Protocol, I think. And it depends on and knows nothing about the lower layers. Okay, so the application layer depends on the lower layers. It doesn't know anything about the lower layer. Now here's a somewhat hairy little picture. It's an example of part of an email message that I received using Gmail. And you can do this if you use Gmail. You can just click on the words Show Original. I think there's a little button that says Show Original on the Gmail menu to see the raw content that the application would send to the transport layer. And this, it's not color-coded by default. I mean, I have a program that applies this color coding. And the color coding is this, that the orange part is the names of the parts, and the blue and white parts are the values of the parts. Now the above scheme, this layering scheme, is very loosely defined on purpose, and that loose definition leads to my use of words like sorta and kinda. The scheme is more or less formalized in RFC 1122, and there's a diagram on the Wikipedia page for the Internet Protocol suite of that scheme, which is called the IP stack connections. And many people disagree with its looseness and ambiguity and other limitations. And we're not going to talk about their fabulous replacement strategies, even though one of those strategies will probably someday replace the Internet Protocol suite. But again, it hasn't done that for over 30 years. So let's just talk about reality. Now, this change, I said, is inevitable because we're running out of addresses. But we have a technique called network address translation, a technique for staving off the inevitable change to IPv6. So there are public addresses, and there's a hard limit on these because everyone can see them, but there are also private addresses, and any address that starts with either 192.168 or 10 is a private address, invisible outside the local area network. That's a hard and fast rule. And a device that's on a LAN can have a private address that's known only to your router, or cable modem if you want to use a marketing term. And that router has one public address for your entire household or whatever it's connected to. And all the traffic from the internet goes through that one public address. And the router translates it to an internal address. And again, that router could be called a DSL modem or a cable modem or some other marketing term. One thing that we might want to do is send video. In fact, increasingly, most of the traffic, packet by packet, going across the internet is video. And so we can use network address translation to deal with that. So we have a thing called a socket that contains a sending device's IP address and port number. For example, 129.21.50.10:24010, and that 24010 is called a port number. And a port is a convenient way to organize communication between a computer and the outside world without the computer having to waste a lot of time listening for signals to or from the outside world. So there's specialized hardware involved that allows us to send video packets without much overhead. Now there's plenty of detail that we could go into besides this. I've just given you a sample of some little bits of detail. And you can just Google the terms TCP/IP, IETF, IP addressing, and network protocols, and you can look on YouTube for tutorials on these most basic topics. You can also Google terms like Internet 2, latency, domains, host, and top-level domains if you want the most common of the more advanced topics. Okay, so the top group here that I mentioned are kind of basic topics. The bottom row here is more advanced topics. There are plenty of books and websites that you can use. By far the best, there are two that are by far the best. They're both written by W. Richard Stevens. Unfortunately, he passed away right after he wrote them, probably in the early 1990s. And so the books are old. I think at least one of them, though, has been updated by some other people, although it still lists W. Richard Stevens as the author. And his two books on TCP/IP are very practical and very detailed. And these network people tell me that these are the best books ever written on the internet. And at least one of them is available free online. I've seen it online. It's old, and Stevens passed away, and he was not really interested in making money on his books anyway. The other book, which is available online, not for free, is more academic. So that's Andrew Tannenbaum. Not to be confused, I think there's also an Andrew Tannenbaum, so this is spelled slightly differently. And Tannenbaum wrote the most widely used networking book. There's also a Tannenbaum who's written some other computer books that are good, that are, a prominent author. Not to take anything away from him, but the most prominent academic network book, if you were to take a course to go into a lot of detail on networking, I would rely on that book rather than on, Internet for Dummies or, how to do the internet in 20 days or stuff like that. These are the authoritative sources. Now, obviously, the web is part of the internet, and the Wayback Machine at the Internet Archive attempts to be a record of all web pages throughout history. So it is possible to find, it's possible to find almost anything. Of course, they can't. It's not really a record of all web pages throughout history. They sample the web at intervals, but you can get a lot of information about what how the internet looked through the Wayback Machine. Now I'd like to ask you a few exam questions. And these are not for your exam. These would be for an undergraduate class. And it's for the kind of people who will be doing technical tasks. And you have to rub shoulders with these people. I'm assuming that you are going to be doing policy-related tasks and decision-making tasks. But you have to be able to work with people who do technical tasks. So I want you to have a general idea of the kinds of technical things that they know. So I'm just going to give you some about 3 sample questions here. And the first question is, and of course the answers as well. And the first question is, suppose that I display my network configuration status as follows. What is my Internet Protocol version 4 address in binary? And if I have a machine running Mac or Linux, I simply open a terminal window and type the word ipconfig, IPCONFIG, in the terminal window, and I'll get a display similar to this. On Windows, it's a little bit more complicated, but something similar will give you a window like this. The correct answer requires you to first see which network interface is active. So there are 2 network interfaces displayed. One is the P2P0 interface, and the other one is the EN3 interface. And at the bottom under the EN3 interface, you'll see status active. And so EN3 is the active interface. Then search within the EN3 entry for the string INET, I-N-E-T. And you'll see next to it the IPv4 address, 129.21.217.106. So that is your Internet Protocol version 4 address in decimal. And now you have to convert decimal numbers into binary without the aid of a calculator, because on an exam I wouldn't allow a calculator because I want to verify that students understand binary numbers. Binary numbers are sums of powers of 2, And the relevant powers of 2 for this question are the ones that go from 2 to the 0th power, which is equal to 1, to 2 to the 7th power, which is equal to 128. And if we were to add all of those numbers together, if we were to add 1 times each of those numbers together, we would get 255, which is the largest number that we can have in one of these 4 octets. So we convert each of the 4 numbers between dots into ones and zeros separately. So for example, the first one is 129, and 129 is equal to 128 plus 1. So its representation as a binary number would be based on 2 to the 7th, which is 128, plus 2 to the 0th, which is 1. So in 8 bits, we would represent that as 10000001. And I usually leave a space between every 4 bits because I have trouble reading across. So using this same method, we're going to do all 32 bits. So we can read the preceding number, that number 10000001, as 1 times 2 to the 7th power, plus 0 times 2 to the 6th power, plus 0 times 2 to the 5th power, plus 0 times 2 to the 4th, 3rd, 2nd, and 1st powers, plus 1 times 2 to the 0th power. Now we can do similar calculations with the other numbers, 21, 217, and 106. And in each case, we'll get an 8-digit or an 8-bit number, an 8 binary digit number. We abbreviate binary digit as bit. And so the complete answer is 32 bits long. It's the 8 bits of the 127, followed by the 8 bits of the 21, followed by the 8 bits of the 217, followed by the 8 bits of the 106. So we get that as our correct answer to the question, what is my IPv4 address in binary? When I send a picture using the internet, which of the following does the link layer know about? How to move my packets through the local network, how to divide my file into packets, how to divide my packet into files, how to move my packets through the internet, and how to package my picture into an appropriate file. So this is a multiple choice question. So the answer is one of those 5 questions, and I would expect someone who's working with the internet in a technical manner to easily be able to discern which of those is the correct answer. The correct answer is, of course, the first choice above. And here's more detail on each choice. So the link layer knows the local network architecture and can tell where in the local network is closer to a goal that lies across the internet outside the local network. The second answer, how to divide my file into packets, is the transport layer's job. The third answer, how to divide my packet into files, is just nonsense. No one knows how to divide my packet into files. It's just made up answer. Then how to move my packets through the internet, that's the internet layer that knows how to do that. It moves packets across the internet, but not within any given network along the way. So the application layer knows how to package a picture into a file that is appropriate to send to the transport layer. So for example, an email program knows how to package it in an email, which is one of many kinds of files that can be understood by the transport layer. And finally, how can I mask my IP address at RIT to address an RIT service whose final 2 IPv4 octets are both 255? And we touched on this before. This is just going into a little bit more detail. The correct answer is to mask my IP address so that only the 129.121 part, 129.21 part is shown, and the remaining 2 parts are both converted to 255. So we can think of this, I think I said before, that we can think of this 129.21 as my street address, and the other 2 parts, 217.106 as my apartment number, and I suppose I would like to have mail delivered to a building-wide mail drop rather than directly to my apartment, assuming that the building-wide mail drop has somebody that knows the individual apartment numbers. So that's sort of the use case for this. So the question is, what operations and masks will accomplish this? And the operation is OR. So the OR operation will turn some bits on no matter what they are now, depending on what mask we use, and it will leave some bits alone no matter what they are now, depending on what mask we use. So OR with a mask of 0000 and so on for we'll leave the first half alone, or with a mask of a bunch of zeros, we'll leave the 129.21 alone, and with a mask of 11111 and so on, we'll convert the 217.106 to 255.255. In other words, it will turn all those bits on, so it'll be the sum of all of those powers of 2. So, and that is the address of a certain service on my subnet. So this masking prevents individual nodes on the internet from having to know anything about the last 2 octets of my IP address, just that the standard services are located at standard addresses on any subnet. Okay, that's a wrap for our discussion of the internet in general. When next we meet, we'll talk about, more specifically, the Internet of Things. So I'll look forward to seeing you then, and thanks for your attention.